So, good evening, students. So, today we discuss problems from electromagnetism. So, this is the first question. A steady current is set up in a cubic network composed of wires of equal resistance and length d as shown in the figure. What is the magnetic field at center P due to cubic network? So, this is a cell connected and this is a cubic network, all of them equal resistors, and cell is connected across H and C. So, what is current in each branch will be, this is I by 3, I by 3, I by 3 if I get, here I by 6, if current here is, let us say I, then what is current here? I by 3 I will get, and here also I by 3, here also I by 3, then here it divides I by 6, I by 6, and here also I by 6, and here I by 6, and here also I by 6, and here it is I by 3 once again, here also I by 3, and here also I by 3. So, here I by 3 and here I by 3, there are two wires, parallel wires, equidistant from point P, carrying same current, and similarly here I by 6 and exactly opposite to that, parallel to that, is also I by 6. So, when there are two wires which are parallel to each other carrying same current, then what is magnetic field at midpoint? Is 0. Due to this, magnetic field is going into, and due to this, magnetic field is coming out. So, for every wire there is exactly parallel wire where P is midpoint carrying current in same direction and same current, then what is magnetic field at center will be 0. So, due to each wire, due to two sets of wire, it is 0. So, total magnetic field is also 0. Okay. Any doubt? The next question we'll see. Next is this question. A small block of mass m having charge q is placed on a frictionless inclined plane making an angle theta with the horizontal. There exists a uniform magnetic field B parallel to the inclined plane but perpendicular to length of the spring, and magnetic field is going into here, parallel to the inclined plane and going into. If m is slightly pulled on the incline in downward direction, the time period of oscillation will be, assume that the block does not leave contact with the plane. So, what is charge on that block is q, and we assume it is a point charge. Then as it is oscillating like this, magnetic field is going into, and velocity is parallel to the inclined plane, and magnetic field is going into. Then what is force due to magnetic field? It is given by q into v bar cross b bar. It is always perpendicular to velocity at each and every point. So, it won't do any work and it won't develop any power. Then what is the direction of force is like this, v bar is in this direction, v bar is going into. So, force is upwards when velocity is down the plane, and as it oscillating, velocity can be up the plane also sometimes. When velocity is up the plane, then force is downwards. So, force due to magnetic field sometimes it will increase normal force, sometimes it will decrease normal force. So, there is a possibility it may get lifted up, but in this case that possibility is ruled out. So, if it is oscillating, the force due to magnetic field is always perpendicular to inclined plane. So, that do not have any effect on frequency of oscillation. Okay. So, what is frequency of oscillation? Only depends on spring constant, and other force is mg sin theta, which is a constant force, and frequency do not depend on constant force for linear SHM. Okay. So, what is omega? I will get omega is root k by m, angular frequency, and time period 2 pi root m by k I will get. Okay. 2 pi root m by k. So, answer is A, I will get 2 pi root m by k. Okay. Now, a long cylindrical wire of cross section radius r carries a current density J bar along axis such that J bar is J naught into 1 plus small r by capital R, where J naught is a constant, r is distance from axis. Small r is less than capital R. Find magnetic field strength at small r equal to r by 2. Okay. So, there is a long cylindrical cross section of wire of radius r. Current density is J bar along the axis of the cylinder. Okay. So, if there is a solid cylinder, if there is a solid cylinder, there is a solid cylinder, if it carries a current I along the axis of the cylinder, where current density is given as some function of r, function of radial distance measured from axis of the cylinder, then how to find magnetic side at a distance r? So, we have to use Ampere rule, Ampere law. So, at a distance r, if you have to find magnetic field inside, we should construct an Ampere loop, a circular loop whose center is on the axis, and by symmetry magnetic field at each and every point of this loop should be same in magnitude and along the tangent. Then integral b bar dot dl bar for that loop can be written as b into length of the loop, that is 2 pi r, that is equal to mu naught into current enclosed by that loop. How do you find current enclosed within this loop? If current density is constant, then it is J into pi r square you can do, where J is total current across the cross section by pi capital R square, by cross sectional area of the cylinder, that we can find. If they directly give J, it is J into pi r square if J is constant. But if they give current density as a function of R, then how to find current within this Ampere loop? Then we have to divide this Ampere loop into small circular rings with small width. Okay, circular rings with small width. Then what is current within that loop is integral 2 pi r dr into whatever function they give, f of r, from 0 to small r. To small r. If I integrate, I will get current enclosed within this loop. Then that you have to put here, mu naught into current enclosed. Okay. Then relative permeability is 1 we will take in such cases, unless they mention something. Then you will get mu naught into mu r. Okay. So, b into 2 pi r equal to mu naught into current enclosed. So, in this case what they have given, current density as a function of r is J naught into 1 plus small r by capital R. If I substitute that, then what do you get? What is I enclosed? Integral 2 pi into r into f of r, that is J naught, also you can take it out of integration, then r plus r square by r dr from 0 to small r. Okay. Then what do you get? 2 pi J naught into r square by 2 plus r cube by 3 will get. R cube by 3r, that is what you will get. Okay. And now if I substitute that here, what is b will get? 2 pi cancels. So, what is b? Divided by r. So, that is J naught into r by 2 plus r square by 3r. So, that is magnetic field as a function of r inside. Outside anyhow it is mu naught I by 2 pi small r, where I is total current passing through any cross section of the cylinder. Total current you can find by integrating this from 0 to capital R. Okay. So, any doubt in this? So this is magnetic field inside. What is magnetic field outside? R greater than or equal to R. Magnetic field outside is given by mu naught I by 2 pi R, okay, as a function of radial distance. And small r equal to capital R, both the formulae coincide. Okay. What type of graph you will get? Magnetic field versus radial distance. Inside it is parabola. R square term is there. It's a parabola. Outside it is inversely proportional to R. Okay. And it is continuously increasing. Okay. Inside. So its axis magnetic field is 0. Okay. So what is magnetic field inside? It is J naught into R by 2 plus R square by 3R. J naught into R by 2 plus R square by 3R. And outside mu naught I by 2 pi R. So what type of graph here? Magnetic field versus radial distance. Small r equal to R by 2 they have asked in the question, that we can find. Okay. Let's substitute. At R equal to 0 it is 0. Then as R increases, magnetic field also increases, and we will get a graph like this. Whose slope is also increasing. If I differentiate this with respect to R, we will get 1 by 2 plus 2R by 3R. So as R increases, slope is also increasing. We will get a curve like this until capital R, where magnetic field is mu naught I by 2 pi R, where I is total current. Then afterwards, magnetic field is continuously decreasing like this as R increases. Magnetic field decreases inversely proportional to R. So any doubt? See that question? Any doubt is there, you can ask. Okay, completed. See next question. This is the next question. A long straight wire carries a current I. A particle having a positive charge Q and mass m kept at a distance x naught from the wire is projected towards it with a speed v. Find the minimum separation between the wire and the particle. So there is a long wire which carries a current I, and there is a particle whose charge is positive, charge is q, and mass is m, kept at a distance x naught from wire, and is projected towards with a speed v. Then what is the direction of magnetic field due to that wire? It's a variable magnetic field, because due to long wire it is mu naught I by 2 pi x. Magnetic field towards left of this wire is coming out towards you, and magnetic field towards right of the wire is going into. So here magnetic field is coming out here, and velocity is towards right. So force downwards will get v bar cross b bar. It's a variable force, but force is downwards. So it will follow a path like this and come like this. And when separation is minimum, what is the condition? Condition is angle between r bar and v bar is 90 degrees. When separation between this wire and this particle is minimum, then angle between v bar and r bar at that instant is 90 degrees. Means by that time the velocity vector has rotated by 90 degrees. Okay. So in between, let us say when particle is somewhere here, its velocity is in this direction. Velocity is changing here because of force due to magnetic field, but speed do not change. So initially what is speed of the particle is v, and at any instant its speed should be v. So at some position, if angle is theta, when particle is at a distance x from here, then what is x component of velocity at that instant is v cos theta, which is given by dx by dt. V cos theta is dx by dt. Okay. Then what is omega? Bq by m. That is d theta by dt. That is bq by m at that instant. What is b? Mu naught I by 2 pi x into q by m. Okay. So from these two equations, what do you get? Dx by d theta. This will be negative anyhow. Dx by dt will be negative, because as it is going like this, what happens? X is decreasing. X is decreasing. So I will put a minus sign here. Okay. And now if I divide these two, what do you get? Dx by d theta equal to, if I divide these two, minus v cos theta by mu naught I q by 2 pi m x I will get. Okay. 2 pi m x. Okay. Two pi m x. And now from here you can find, you bring this x to LHS and d theta to RHS. Okay. So then what do you get? Dx by x equal to 2 pi m v by mu naught I q with a minus sign into cos theta d theta. Now when x is minimum, initially what is theta? 0 degrees. When x is minimum, theta is pi by 2. So what are limits of integration for theta? 0 to pi by 2. And for x, initially x naught, finally x. Okay. So if I substitute the limits, what do you get here? Log x by x naught equal to, if I integrate cos theta d theta, I will get sin theta. If I substitute the limits, I will get 1. Sin pi by 2 minus sin 0, that is 1. Okay. So minus sign will be there. So log x by x naught equal to this cell. What is x? X naught into e to the power of minus 2 pi mv by mu naught IQ. So that is the minimum distance. Followed or any doubt? Any doubt? So the force due to magnetic field, it won't do work. Okay. It do not change any kinetic energy. It will change momentum. Only direction of momentum it will change on a moving charge. Okay. And all these are steady magnetic fields. Time varying magnetic fields, they will produce electric fields. So they will do work on moving charges. And these are varying magnetic fields, but they vary with position. Such magnetic fields are called steady magnetic fields or stationary magnetic fields, which are varying with position and not varying with time. Time varying magnetic fields will produce electric field. Then they can exert force on stationary charges also, and they will do work also. Okay. So next question we'll see. Now this is the question. A magnetic field B bar equal to B naught J bar exists in the region A is less than X is less than 2A, and B bar equal to minus B naught J bar in the region 2A is less than X is less than 3A, where B naught is a positive constant. A positive point charge moving with a velocity V naught I bar, where V naught is a positive constant, enters the magnetic field at X equal to A. The trajectory of the charge in this region can be like, now this is X axis and this is Y axis, or this is Z axis, I think they did not mention. the figure, but that is z axis. Okay, in the question they have mentioned. Okay, choices, this is z axis. Now this is z axis, this is x axis. Then what is the direction of positive y? Positive y is going into k bar cross I bar. Okay, so positive y is going into, negative y is coming out. So positive y is going into, negative y is coming out. Okay. So initially, what is the direction of magnetic field? B naught j bar means magnetic field is going into between A and 2A. So between these 2 points. Okay, a positive point charge, it has entered with a velocity v naught I bar in this direction. But once it comes to point A, it will experience force due to magnetic field, and that force will be in what direction? Velocity is towards right, and magnetic field is going into between A and 2A. So force is upwards, and it's a constant magnetic field, so it moves along a circular path. So path will be somewhat like this until it reaches 2A. Until it reaches 2A, and once it comes to 2A, what happens? Velocity will be in this direction, but magnetic field direction has changed. It is along magnetic field at x equal to A. The trajectory of the enters the magnetic field at x equal to A. The trajectory of the particle can be, it is minus b naught j bar between A and 2A. A and 2A it is minus b naught. Between A and 2A it is b naught j bar, and between 2A and 3A it is minus b naught j bar. Minus b naught j bar means what? Once it comes to 2A, magnetic field is towards you, and velocity is in this direction, magnetic field is in this direction. So force will be like this. So force is in this direction at that instant. So it will follow some path like this. So between A and 2A it follows a path like this, and from 2A to 3A it will follow a path like this. Okay. So A is correct answer. Okay. So next question we'll see. Next, this is the question. An infinitely long hollow conducting cylinder with inner radius r by 2 and outer radius r carries a uniform current density along its length. The magnitude of magnetic field B bar as a function of radial distance r. So this is also like just similar question as we have done earlier, but there current density is varying. In this case it is a uniform current density, but it is a cylindrical shell of some inner radius r by 2 and outer radius r. Then what is magnitude of magnetic field as a function of radial distance r? Outside it is mu naught I by 2 pi r anyhow, outside, and up to r by 2 magnetic field is 0. So you should get along x axis up to r by 2. Then later between r by 2 and r there will be a magnetic field which is varying, and after capital R magnetic field is inversely proportional to r, so it will decreases with increase in distance, and as r tends to infinity magnetic field tends to 0. Okay. So between r by 2 and r we have to find that sum. So between r by 2 and r, what type of magnetic field you will get? It is a cylindrical shell. What is inner radius? R by 2, outer radius r, and current density is constant. So let us say current density is J, that is constant. So at a distance r from center, how to find magnetic field? If I consider an ampere loop of radius r, then integral b bar dot dl bar can be written as b into 2 pi r once again, and that is equal to mu naught into current enclosed within this loop, because J is constant. What is current within this loop? Is current between these two circular loops, means area between these two circles into current density. What is that area? Pi into, this is r square by 4, and outer area is pi small r square. So what do you get? Mu naught into pi small r square minus pi r square by 4 into J. So what is B? If I cancel pi, B is mu naught by J by 2 into r minus r square by 4r. So this is what it. Okay. Set small r equal to r by 2. What is magnetic field? We can find. Small r equal to r by 2. What is magnetic field? If I put capital R by 2, here capital R by 2, here small r by 2, so 0 I will get. Small r by 2. Capital R by 2, if you put capital R cancels, then 2 also cancels, it will be 0 at that point. Then from there, at small r equal to capital R, what is magnetic field? You put small r equal to capital R here. Then what do you get? Capital R minus r by 4 will get, that is 3. Capital R minus r by 4, that is 3r by 4. So mu naught J by 2 into 3r by 4 will get, that is magnetic field on the circumference. Okay. In between, how magnetic field is varying now? So what type of graph you will get? Up to r by 2 magnetic field is 0. Between r by 2 and r, is it continuously increasing or decreasing? What is dB by dr? This is 1 minus plus I will get r square by 4r square, 1 by r if I differentiate. So dB by dr is positive. As r increases, magnetic field is continuously increasing. Okay. As r increases, magnetic field is continuously increasing. But what about dB by dr? As r increases here, what about dB by dr? Is decreasing. As r increases, dB by dr is decreasing. Okay. So what type of graph here? Up to r by 2, 0. Then from there, it will increase. Magnetic field is continuously increasing. Okay. But slope is decreasing. So you will get a graph like this. Okay. These are the graphs they have given. We can identify. Next, up to capital R. And afterwards, it is inversely proportional to R, like this. If slope is increasing, we will get a graph like this. If slope is decreasing, we will get a graph like this. Okay. Followed. Okay, next question. Now this is the question. A conducting ring of mass 2 kg and radius 0.5 meters is placed on a smooth horizontal plane. Smooth horizontal plane. This is smooth horizontal plane. But conducting ring is in vertical plane. Conducting ring is placed like this. Okay. The ring carries a current I equal to 4 ampere. The horizontal magnetic field B equal to 10 Tesla is switched on at t equal to 0 as shown in the figure. The initial angular acceleration of the ring. So there is a magnetic field like this and there is a current in the wire, maybe clockwise or anti-clockwise. So if current is like this, then magnetic moment is going into. What is magnetic moment? I into A. If number of turns are given, you can find that. So magnetic moment is going into, and magnetic field is in this direction. Then torque due to magnetic field is m bar cross b bar, that is like this. So this disc or ring, it starts rotating like this. So about this axis, ring starts rotating like this about this axis because of this torque m bar cross b bar, but m bar is going into, b bar is in this direction. So initially what is angle between them is 90 degrees. So initially what is m bar cross b bar magnitude is m into b, you can write. So I into a into b, that is torque, that is equal to moment of inertia into alpha. What is moment of inertia of a ring about diameter? About axis it is m r square, about diameter it is m r square by 2 into alpha, that is it. But area is pi r square, okay. R square cancels, so what is alpha? 2 pi I b by m. So that is angular acceleration, okay. So what is I given? 4 ampere. Radius is not required, I think. Mass is 2 kg. I is 4 and mass is 2 kg means this is 2 will get. And magnetic field is 10. So 40 pi will get, okay. 40 pi radian per second square. Next, a wire of cross sectional area A forms 3 sides of a square and is free to rotate about axis O prime. If the structure is deflected by an angle theta from vertical, when the current I is passed through it in a magnetic field B acting vertically upwards and density of wire is rho, then the value of theta is given by, okay. Now this is deflected by an angle theta. Initially wire is in a vertical plane, it can rotate about this axis, and there is a magnetic field switched on like this, okay, and current I is passed. When current I is passed like this and magnetic field is coming out, let us say m bar is towards you, then m bar cross b bar is like this, then it starts rotating like this. M bar cross b bar is in this direction, so torque is along O prime to O, then it starts rotating like this. Then if there is a current I, when this plane is in vertical plane initially, then we have given a current I and maintained it. Then what is the angle it turns instantaneously? Means we have to do by energy method. And finally, what is the angle this wire makes with vertical in equilibrium position? Means torque is 0, will write, when net torque is 0. So it rotates by an angle theta finally, when net torque is 0, that is the equilibrium position. But initially when it is here, where it is in equilibrium by rotating an angle theta, there it will acquire maximum angular velocity. Then it still rotates by another theta and stops there. Okay, so instantaneously what is the angle it goes before it stops and oscillates like this finally? That if they ask, then you have to do by energy method, or you can take the position where net torque is 0 and double it, also you will get that, okay. So in this case, what is magnetic moment? Magnetic moment is, if each side length is L, then it is L square into I. L square into I, that is current, okay. Density of wire is rho, they have given, okay. And what is A? Wire of cross sectional area A, they have given, okay. 3 sides of a square and is free to rotate about O prime, okay. What is length? L. Then 3 sides they have given. Then 3 into L into A is total volume, okay. To density if I do, you will get mass, okay. Total mass. What is mass of each part of the wire? Is L into A into rho, okay. This part of the wire, this part of the wire, this part of the wire. Then in equilibrium if they ask, once it rotates by an angle theta like this, initially in this position, if current is in anti-clockwise direction, magnetic moment is coming out m bar and magnetic field is in this direction. What is the angle between them? 90 degrees. From there if it rotates by theta, then angle between m bar and b bar will become 90 minus theta. 90 minus theta after it rotates by theta. So if I draw the side view now, that entire frame rotates by an angle theta about O prime, okay, about this line. And where is center of mass? Total, what is mass of each part of the wire? That is m I have taken. And where is center of mass? Total gravitational force is 3 mg, and that will act at center of mass. Where is center of mass of this part of the wire? Is at a distance of L by 2, and for this part of the wire at a distance of L by 2 from here, and for this part of the wire here at a distance L. So what is total mass here? 2m. I can keep it here. This is L by 2, and m is here at a distance L. Okay. Then what is distance between these two? Is L by 2. L by 2. Then where is center of mass from here? Inverse ratio of masses, the distance. So from 2m at what distance? Is 1/3 of L by 2. So it rotates by an angle theta until the torque due to gravitational force is balanced by torque due to magnetic field. What is torque due to magnetic field? Is m into b into sine theta, where theta is angle between m bar and b bar. In this position, angle between m bar and b bar is 90 degrees, and by the time frame rotates by theta, angle between m bar and b bar has become 90 minus theta. B bar will be in this direction only. Okay. So 90 minus theta. So what is torque due to magnetic field? Is m into b into sine theta. M into b into sine of angle between m bar and b bar, which is 90 minus theta. So cos theta I will get. So m is L square I into b into cos theta equal to torque due to magnetic field. That is 3 mg into this distance. That is 2L by 3 into sine theta. Okay. So tan theta equal to this L. And what is m? LA rho, you can substitute. M is equal to L into A into rho. L square cancels, I will get. And instantaneously, what is the angle? If they ask, it will be double that angle. Another theta. That will be oscillating like this. What is the angular amplitude? Is theta, not SHM, unless theta is very small. Okay. Not angular SHM, unless theta is very small. Followed or any doubt? And if they ask, what is angular velocity? What is maximum angular velocity? When it is released here initially, what is maximum angular velocity? Where will it acquire maximum angular velocity? It will acquire maximum angular velocity when it is passing through mean position, where net torque is 0. That is this position, where tan theta is given by that equation. Okay. Then from here to here, we should apply work done by gravity plus work done by the torque due to magnetic field. Okay, is equal to change in kinetic energy. Okay. So what is work done by gravity will be negative, and work done by torque due to magnetic field is positive. What is work done by torque due to magnetic field? What is torque due to magnetic field? It is m into b into sine 90 minus theta, that is cos theta. So it is m into b into cos theta. And what is m? I into L square. This you have to integrate from, what is theta? Theta is the angle turned. Okay. So initially 0 degrees. So 0 to theta. This theta is whatever you have found out earlier. Okay. In equilibrium position. So this is work done. How much is it? That is bi L square into cos theta. If I integrate, you will get sin theta. That is sin theta. Okay. What is torque? BIL square cos theta when frame has rotated by an angle theta. That is torque. This torque you have to integrate with respect to theta to get work done from 0 to this angle. Okay. So 0 to this angle. If I integrate, you will get this. This is work done by torque due to magnetic field. What is work done by gravity? Its total mass is 3m into center of mass as raised by 2L by 3 into 1 minus cos theta equal to half I omega square. That's it. Then you can find omega, the maximum angular velocity. What is I? Moment of inertia. What is moment of inertia? This is the frame and this is the axis. What is mass of each part is m and length of each wire is L I have taken. Then what is moment of inertia? For this part ml square by 3, for this also ml square by 3, that is 2ml square by 3 plus for this part ml square. That's what. So if they ask what is maximum omega also, you can find like this. Maximum omega is when net torque is 0. It will travel double the distance and stop. If I equate this to 0, we will get instantaneous angle turned by the frame. Okay, next question is. This is the question. In figure, a coil of single turn is wound on a sphere of radius r and mass m. The plane of the coil is parallel to the inclined plane and lies in the equatorial plane of the sphere. If the sphere is in rotational equilibrium, the value of B is. Current in the coil is I. So if current in the coil is I and it is in rotational equilibrium, current can be as seen from top. Current can be clockwise or anti-clockwise. It can be clockwise or anti-clockwise. Okay. So magnetic field is in this direction. So if I resolve magnetic field perpendicular to coil or perpendicular to the inclined plane, that is B cos theta I will get. What is this angle is 90 minus theta and this is theta. So this is B cos theta and in this direction B sin theta I will get. Okay. And magnetic moment is in this direction. Coil is parallel to inclined plane. So magnetic moment is perpendicular to the inclined plane. Okay. So if I do m bar cross b bar, due to this component of magnetic field, torque is 0. Due to this component of magnetic field, there will be a torque. So if current is in clockwise direction, if you see from top, magnetic moment is in this direction. Then m bar cross b bar is in this direction. So the torque due to magnetic field produces anti-clockwise moment. It produces anti-clockwise moment about center. If magnetic moment is in this direction. Okay. And because this is in equilibrium, net force has to be 0 and net torque is 0. Okay. Net force has to be 0 and net torque is 0. Now what are the forces acting? One is mg sin theta, the component of gravitational force. Normal force will be in this direction. Mg cos theta is in this direction. And frictional force will act in this direction. We should balance mg sin theta. Okay. And torque due to magnetic field do not depend on axis of rotation. So torque about any point you can take. So torque about this point if I take, which should be 0. Then torque due to mg sin theta, it produces clockwise moment. So that is mg sin theta into r. That should be balanced by torque due to magnetic field. That is m into b. M into this component of b, that is b sin theta. Magnetic moment into b sin theta. What is magnetic moment? Is I into pi r square into b sin theta. Okay. So what is b value you can find from here. Okay. Sin theta cancels. You can find b. And what should be the direction of current here? If you see from here, it should be clockwise. Magnetic moment is going. Okay, completed. The next question we'll see. Next is this question. A conductor AB of length L carrying a current I prime is placed perpendicular to a long straight conductor XY carrying a current I as shown in the figure. The force on AB has a magnitude of. So this is a long current carrying wire I, and there is a straight conductor here of some length L, and this distance is L by 2, and it carries a current of I prime. And what is force of interaction between them? So due to this wire, magnetic field at each and every point is not same anyhow. So we have to integrate by considering some small current elements. So at a distance x, if I consider a small current element of width dx, then what is magnetic field at that point is mu naught I by 2 pi x, and magnetic field is going into due to this, and current element is in this direction. So force due to magnetic field is upwards, and on this entire wire it is upwards only. So net force means you have to integrate. Okay. So what is force on this small element is I prime dx. Then how do you find total force? You have to integrate as x varies from L by 2 to 3L by 2. So what do you get? Mu naught I prime by 2 pi into log x will get. And if I substitute upper limit and lower limit, you will get log 3. Okay. Answer is B. Okay. Next question. This is next question. A loop carrying a current I lies in xy plane as shown in the figure. The unit vector k bar is coming out of the plane of the paper. The magnetic moment of the loop. So directly they are asking magnetic moment, and current, as you see, it is anti-clockwise direction. So magnetic moment is coming out. So it should be along k bar. All of them they have given k bar except this one. Okay. So answers can be either A, B or D. Then area I should. What is area of this part? This is a semicircle, and what is radius? A by 2. Diameter is A. So radius is A by 2. So what is area of this? Pi a square by 4 by 2. Area is pi r square by 2. Okay. So pi a by 2 whole square by 2 is pi a square by 8 for this. But 4 semicircles, so into 4. So pi a square by 8 into 4, that is pi a square by 2 plus this square. What is this square? Is a square. So plus a square into I. So that is magnetic moment, and it is along z axis. So k bar. Okay. So a square into pi by 2 plus 1. Okay. Now this question. A non-planar loop of conducting wire carrying a current I is placed as shown in figure. Each of the straight sections of the loop is of length 2a. The magnetic field due to this loop at point a comma 0 comma a points in the direction. Now if I see this is one, each of the straight section has a length 2a. So if this is 2a, this is also 2a, this is also 2a, then this is also 2a. Even though in figure it is not looking like that, this is looking bigger. Okay, but if I take everything is 2a, this is 2a, this is 2a, this is 2a, this is 2a, then this is a square frame element. So there is a current here like this. If I introduce a current in this direction like this, and introduce a current in this direction, now we have two loops. One loop is like this, other loop is like this carrying current. So this loop is in YZ plane, this loop is in YZ plane. Then what is area of each loop? Is 4a square. If this is 2a, this is also 2a, this is also 2a. That's what I am assuming. I don't know, but that's what they have given. Okay. So this is 4a square element. This is also 4a square. And what is current in this loop? If I see from here, is in anti-clockwise direction, and that is in YZ plane. So magnetic moment is coming out. So that is along x-axis. So for this loop, what is magnetic moment? That is 4a square I bar element. And for this loop, if you see from top, that is also anti-clockwise direction. It is coming out, okay, but this is in xy plane, it is coming out, means k bar. So it is 4a square k bar L. So what is magnetic moment? 4a square into I bar plus k bar, okay. So that is magnetic moment, and they are asking magnetic field at a comma 0 comma a. So a comma 0 comma a is axial line for this magnet. I bar plus k bar is axial line. So an axial line, what is the direction of magnetic field? It is like parallel to magnetic moment. So it is along I bar plus k bar, okay. So it is I bar plus k bar by root 2. That is the direction, okay. So next question we'll see. Now this is the question. An infinite current carrying wire passes through point O and is perpendicular to the plane containing a current carrying loop ABCD as shown in the figure. Choose the correct options. So there is a wire like this, it carries a current coming out or going into, okay, coming out I will take, and that current is I, let us say, and there is a current carrying loop here which carries a current like this as shown. Now net force on the loop is 0, that is correct, okay. Now due to this wire, what type of magnetic field I will get if I take current in this direction? Circular magnetic field is in this direction. So everywhere here magnetic field is parallel to current element, so force is 0. Here also unlike parallel to current element, but angle is 180 degrees everywhere, so 0. Now here magnetic field is going into, but variable magnetic field going into, and current element is in this direction, so force is in this direction going into, and current element is in this direction, so force is towards UL, okay. Current element is in this direction and magnetic field here is in this direction, okay. So what is the direction of force? L bar cross B bar. So force is upwards. Similarly here, what is the direction of magnetic field? Like this, and current element is in this direction. L bar cross B bar is going into it. So here force is in this direction, here force is in this direction, and both the forces acts like a couple. So net force will be 0, but it rotates like this. So if I see from here, it will be rotating like this. So it is rotating in clockwise direction, okay. So net force on the loop is 0 is correct. Net torque on the loop is 0 is wrong. As seen from O, the loop rotates clockwise, that is correct, okay. Rotates clockwise. It rotates like this about this axis. For example, if they give masses, let us say, for this M1, for this M2, and for this M, for this M, and inner radius is A, outer radius is B, let us. Then what is torque? What is torque? And if this angle is 45 degrees, this is also 45 degrees, I will take. Then what is torque? Torque is M bar cross B bar. Torque is M bar cross B bar, okay. What is M bar direction? Current is in, current is like this, okay, in this loop, but M bar is not same everywhere, okay. So what is force here at a distance x from here? If I consider a small element of width dx, what is force will be in this direction, and what is magnetic field at that point? Mu naught I by 2 pi x. Mu naught I by 2 pi x into this I, and current in this loop is small I will take, okay. Then it will be I dx, that is force. That force is in this direction here, okay. And here going into that force. And same magnitude of force, if I take corresponding elements, here also x, here also x, then what is distance between them? If I drop a perpendicular, okay, this force is F dF like this force is dF like this, then what is torque due to those two forces? Is dF into this distance, okay. So if this is x, okay, and what is this length? X by root 2, this is also x by root 2, so this is root 2x, okay. So what is torque? Into root 2x, force into perpendicular distance. How do you find total torque? Integrate this as x varies from A to B, you get total torque. Okay. What is total torque? Mu naught II into root 2 by 2 pi into dx, that is B minus A, that is total torque. Okay. Followed? Any doubt? Then if they ask alpha initially, this torque is equal to I alpha, moment of inertia into alpha. Okay. Moment of inertia about this axis here. Okay. For this part of the circular arc, this part of the circular arc, and this part of straight wire, this part of straight, equal to I alpha. Okay. Next, this is the question. A particle of charge plus q and mass m moving under the influence of a uniform electric field EI bar and a uniform magnetic field BK bar follows a trajectory from P to Q as shown in the figure. The velocities at P and Q are VI bar and minus 2V I bar, minus 2V J bar, I think. Okay, this is VI bar and here in the figure it is minus 2V J bar, I think. Okay. Which of the following statement is correct? E equal to 3 by 4 mv square by qa. Now when this particle goes from here to here following some path, then magnetic field won't do any work, entire work is done only by electric field, and force due to electric field is constant because electric field is constant. So force due to electric field is constant and it is along x axis. What is force due to electric field? Is Eq along x axis. So by the time it comes from here to here, what is work done by electric field? Is Eq into 2a, force into displacement in the direction of force, that is Eq into 2a, that is equal to change in kinetic energy, that is half m into 2v whole square minus half m into v square, that means 3mv square by 2 will get. So what is E value? 3mv square by 4qa will get. So this is correct. Okay. Rate of work done by electric field at P. Now rate of work done by electric field means what? Power. That is dot product of force due to electric field and velocity. What is force due to electric field at this point? Is EQI bar, and velocity is also along x axis, that is VI bar. So what is rate of work done by electric field at this point? Is EQ into V. So this is you should multiply this with Q and V. Okay. So 3 by 4 m V cube by A will get. So that is wrong, I think. No. Okay. No V cube. Next, rate of work done by electric field at P is 0. That is wrong. Rate of work done by both fields at Q is 0 is correct. Now rate of work done by magnetic field at each and every point will be 0, because at each and every point the force due to magnetic field is perpendicular to velocity. Okay. But at this point, because velocity is perpendicular to electric field, the rate of work done by electric field is also 0 at that instant, and magnetic field rate at which work is done is always 0 at any instant. Okay. So this is also correct. Now this question, a metal wire PQ of mass 10 grams lies at rest on two horizontal metal rails separated by 5 centimeters as shown in the figure. A vertically downward magnetic field of magnitude of 0.8 Tesla exists in this space. The resistance of the circuit is slowly decreased from, and it is found that when resistance goes below 20 ohm, the wire PQ starts sliding on the rails. The coefficient of friction between wires and rails is found to be n by 25. Find n. Okay. So there is a wire, there is a current here. Okay. And what is current? Is 6 by this resistance 6 by R, and as this resistance is decreased, then current increases, then force on this wire will be increasing. So this force is increasing as resistance is decreasing, and at a particular value of that resistance, this force become equal to limiting friction. The next moment it starts moving. Okay. So when resistance goes below 20 ohm, it starts sliding. Okay. The wire PQ starts sliding. So when resistance become 20, the force due to magnetic field is exactly balanced by limiting friction. And because magnetic field is perpendicular to rails, the force due to magnetic field will be horizontal anyhow. Horizontal. Okay. But if magnetic field is in some direction like this, then you should take two components of magnetic field. One of them will be along normal force or opposite to normal force depending on direction of current and direction of magnetic field. Then limiting friction also depends on magnetic field. Okay. Current. But in this case, because magnetic field is perpendicular, it is simple. So I is in this direction, magnetic field is going into, so current element is in this direction. So force is towards right. And what is that force? BIL. That is equal to mu into N. N is mg, we can write directly, because magnetic field force has no component perpendicular to rails. Okay. So from here you can find directly, I think. What is B given? 0.8 Tesla, so 0.8, and current is 6 by 20 into L, length of the wire is 5 centimeters, so 5 by 100 equal to mu mg. Okay. Mu into m into g. M is 10 gram, that is 10 to the power of minus 2 into 10, that is 10 to the power of minus 1. Okay. 10 to the power of minus 1. So this cancels, and how much you will get? 5 into 4, so 40 you will get. 8 by 400 means 50, so 6 by 50 you will get, is 3 by 25. So n is equal to 25. Okay. Next, this is the question. Two circular coils X and Y having equal number of turns and carrying currents in the same sense subtend same solid angle at point O. If the smaller coil X is midway between O and Y, and if we represent the magnetic induction due to bigger coil Y at O as By, and that due to smaller coil X at O is Bx, then find Bx by By. Okay. This distance is D, this distance is D, then if its radius is R, this radius will be 2R, and if this angle is theta, and if this is L, this also will be L. Then what is magnetic field formula due to a circular coil on axis? It is mu naught Ni R square by 2 into R square plus X square whole to the power of 3 by 2. But what is R square plus X square is L square. R square plus X square is L square. So L square whole to the power of 3 by 2, that is L cube L. That's what I will get if this distance. So what is Bx? Because both of them are carrying same current and same equal number of turns, so N and I will cancel anyhow, all of them are constants. So what do you get? C into R square by L cube I will get. And what will be By? C into 2R whole square by 2L whole cube, 8L cube L. Okay. So what is Bx by By? This is 1 by 2L. Get? So Bx by By will be 2L. Okay, followed. That's all I think. So those are the questions, I think. So I can give some questions. You can write down, I think. Okay. Okay, these questions are there. I'll give one more question. Okay. Now this is x-axis we'll take, and this is y-axis, and there is electric field given by E bar equal to E naught minus alpha x I bar, and magnetic field is a B naught I bar, B naught I bar. And velocity, there is a charged particle of charge q and mass m, and initial velocity is minus v naught j bar, that is velocity at origin. Then you can write down question. Now when it is passing through origin, after some time, if it has to pass through origin, find relation between the given quantities. Find relation between given quantities. That is the question. Can you try? So what do you get here? Now because of magnetic field, velocity is in this direction. So because of magnetic field is in this direction. So force due to magnetic field is in this direction. Okay. So it will be moving in YZ plane in a circle. So because of magnetic field, if I draw YZ plane here, this is y axis, this is z axis. Magnetic field is in this, velocity is initially in this direction, and magnetic field is in this direction. So force is in this direction. So center is somewhere here. So it will be moving in a circle like this and coming back here. So because of magnetic field, it will be moving in a circle like this in YZ plane. Each time it completes a circle, it touches, each time it completes a circle, how it is moving in magnetic field. Okay. So velocity is like this, magnetic field is like this, it is force is in this direction. It will be moving in a circle like this. So this is positive z axis. So it moves in a circle like this, YZ plane. Okay. Each time it completes a circle, it touches x axis, touches x axis. If only magnetic field is there, it will be touching origin. But because of electric field, it is also moving along x axis. And because of magnetic field, each time it completes circle, it should touch x axis. Okay. It should touch x axis. So after what time it can touch x axis, let us say t1, that is 2 pi m by bq into some integer n1. So it completes 2 circles and touches x-axis, then n1 is 2. 1 circle and touch x-axis, n1 is 1, or 3 circles, n1 is 3, like that. But along x-axis how it is moving? It is executing SHM. At x equal to 0, there is no velocity along x-axis, and somewhere here at x equal to x naught, if net force is 0 due to electric field, then what is that point? It is E naught by alpha comma 0. Electric field should be 0 at that point, so force due to electric field is 0, and it will stop somewhere here once again and oscillates like this. So because of electric field, its motion is oscillatory motion along x-axis, and because of magnetic field, it will be moving in a circle like this. So combined motion is a helical path, but non-uniform pitch will get anyhow. But because of this motion, what is time period? Force is E naught q minus alpha qx. What is time period? Omega is root alpha q by m. Okay, what is omega? Angular frequency of oscillation, root of alpha q by m. What is time period? 2 pi root m by alpha q. That is time period because of SH. After every capital T seconds, it will touch origin. It will touch origin. Okay. So every time it should touch origin. Okay. So periodically it should touch origin means what? If it completes SHM, maybe 1 or 2 or 3, whenever it completes integral number of oscillations, in the same time it should complete integral multiple of the circular paths. Okay. So n1 into 2 pi m by bq should be equal to n2 into 2 pi root m by alpha. That is the relation. Okay. Each time it completes one oscillation, it will be at origin because of SH. May not be at origin unless in that time it completes integral multiple of circles. Okay. Followed? So that is a relation. So one more question I'll give you, we can work out later, you can ask. Okay. So let us say there is electric field in this direction. It is E naught J bar. This is x-axis. This is origin, and there is a charge q, mass m, and its velocity is in this direction. Is root 2 v naught. Velocity is in this direction, 45 degrees. Root 2 v naught at an angle of 45 degrees. Where v naught is E naught by b naught. And magnetic field is given by V naught k bar. V naught k bar. Then find after what time it touches x-axis first time. Find after what time it touches x-axis first time. So these are the questions. We'll continue next class. Okay.